Welcome. This is a bonus episode, and it might be the most useful one to listen to first. In the preface, Chip Huyen does something quiet but important. He gives you a short list of concepts and says, in effect, you'll be more effective at building AI applications if you already know these. He doesn't explain most of them. He assumes you walk in owning them. And if you don't, the book gets quietly harder. You hit one of these words on page 80. Your brain stalls for a second, and the paragraph slips away from you. So this episode hands you that entire list in plain language before you ever open the book. 19 concepts. And because you're listening to this on a walk with no screen and nothing to look at, I'm going to turn each one into a picture you can hold in your head. A bag of tiles, a hiker in fog, a spam filter, a compass. Pictures survive a walk. Definitions alone don't. Here's why this matters for you specifically. You're building AI applications and you want to be an AI engineer. Chip says, flat out, that fluency in these concepts is an advantage in that job. That's not because you'll be quizzed on them. It's because every real decision you'll make, which model to pick, why your app gives different answers each time, why your search returns junk, why you can run a model but can't fine-tune it, every one of those traces back to a concept on this list. Own the vocabulary, and the book stops being a wall of unfamiliar words and starts being a set of answers to questions you already understand. Let me give you the roadmap. The 19 concepts fall into 4 families. First, probability. 3 ideas that explain why an AI model behaves like a dice roll and not like a calculator. Second, machine learning basics. 7 ideas about how a model learns anything at all. Third, network architectures. 3 ways of wiring a neural network, only one of which runs the modern world. And fourth, metrics. 6 ways of keeping score, of measuring whether your AI is any good. I'll be honest as we go. The book teaches some of these in real depth, and a few it just assumes and never explains. When we hit one, the book skips, I'll tell you, and I'll teach it properly right here, because those are the ones most likely to trip you up. Let's start with probability. The first family is probability, and it rests on a single mental shift. It's the most important idea in this whole episode, so let me state it plainly. A normal computer program looks up or calculates an answer. Same input, same answer, every single time. An AI model does not do that. An AI model rolls weighted dice. When it produces a word, it isn't retrieving the one correct word, it's drawing one out of a whole range of possible words, each with a different chance of being picked. That one fact explains why the same prompt can give you different answers, why models sometimes confidently make things up, and why you can't test an AI feature the way you test ordinary code. The 3 concepts in this family, sampling, determinism, and distribution, are just 3 angles on that single truth. The first concept is sampling. Here's the picture. Imagine the model has a cloth bag full of word tiles. Every word it could possibly say next is a tile in that bag, but the tiles aren't all the same size. After you type "the sky is," the tile for blue is enormous. It fills half the bag. The tile for clear is medium. The tile for green is tiny, but it's in there. The model reaches into the bag and pulls out one tile, and bigger tiles are more likely to come out. That act of reaching in and drawing one tile, that's sampling. Generating a sentence is just doing this over and over. Draw a tile, say the word, reach back in, draw the next. Now, the reason this matters to you as a builder is that you get to control how the model reaches into that bag. There's a dial called temperature. Picture temperature as how hard you shake the bag before you draw. Low temperature, you barely shake it. The biggest tiles sit right at the opening, and you almost always grab the obvious word. The output is focused, predictable, a little boring. High temperature, you shake the bag hard. The small tiles get tossed up to the top, and suddenly the model might grab green instead of blue. The output gets more surprising, more creative, and more likely to go off the rails. There are 2 more controls worth knowing by name. One is called top K, and the other is top P. Both do the same basic thing. Before you draw, they reach in and throw out the unlikely tiles entirely, so you can only pull from the most probable handful. That keeps the model from ever saying something truly bizarre, while still leaving a little room for variety. So when someone hands you a task like, make our AI assistant more reliable, or make it more creative, or make it stop saying weird things, those aren't vague wishes. Each one is a sampling decision. Reliable means lower temperature. Creative means higher. Stop saying weird things means top K or top P. Knowing sampling is the difference between guessing at settings and choosing them on purpose. Remember the bag of weighted tiles. The second concept is determinism, and this one comes with a warning because it's the assumption that quietly breaks your instincts as a software engineer. Determinism means same input, same output every time. It's how all your normal code behaves. 2 plus 2 is 4. Call that function 1,000 times. You get 4 1,000 times. A calculator is deterministic. An AI model is the opposite. Chip defines it by that contrast. The opposite of probabilistic is deterministic, where the outcome is fixed with no random variation. A model, by default, is not fixed. Ask it the same question twice and you can get 2 different answers because, remember, it's reaching into that bag of tiles and rolling weighted dice each time. It's more like a slot machine than a calculator. Loaded dice, but dice. Here's the trap. As a developer, your gut says functions are deterministic. You write a test. Given this input, expect exactly this output. That instinct will fail you with AI. There's often no single golden answer to assert against. You can turn the temperature all the way down and the model becomes nearly deterministic. It'll grab the biggest tile almost every time, but the machinery underneath is still probabilistic. And across different hardware or model versions, you can still see drift. So you design for a spread of acceptable outputs, not one exact string. Internalizing that, calculator versus slot machine, changes how you test, how you cache, and what you promise your users. The third concept is distribution. If sampling is reaching into the bag, the distribution is the bag itself, the full set of tiles and their sizes. Let me give you a sharper picture. Imagine a city skyline made of bars, standing side by side, 1 bar for every word the model could say next. The height of each bar is how likely that word is. After the sky is, there's 1 skyscraper, blue, towering over a few medium buildings like clear and gray, and then thousands of tiny 1-story shacks for every other word in the language. That whole skyline, all the heights together, is the probability distribution. And here's a tidy detail. All the heights add up to exactly 100% because the model has to say something. Now you can see what temperature really does. Turning the temperature up doesn't change the words available. It flattens the skyline. The skyscraper shrinks a little, the shacks grow a little, and lower probability words get a real chance. Turning it down sharpens the skyline. The tall building gets taller and dominates everything. This same picture comes back later in the book in a completely different room. Evaluation. When Chip measures how good a model is, he compares 2 skylines, the real distribution of how language actually works, against the model's predicted skyline. The closer the model's skyline matches reality, the better the model. Same concept, 2 jobs, generating words and grading the model. Why you'll use this? Complaints like, the model is overconfident, or the answers are all too similar, or it keeps giving me the safe, boring response. Those are all statements about the shape of that skyline. And the fixes, like temperature, operate directly on the shape. That's the probability family. A model rolls weighted dice. Sampling is the roll, determinism is what it's not, and the distribution is the dice themselves. The second family is machine learning basics, 7 concepts about how a model learns anything in the first place. Quick orientation, the same one Chip gives. You will almost certainly never train a foundation model from scratch. That's a job for a handful of companies with enormous budgets. So why learn how training works? Because it turns the model from a sealed black box into something you can reason about. When a fine-tune fails, when one model is sharper than another, when you can run a model but mysteriously can't train it, knowing what's happening under the hood is what lets you debug, instead of guess. Let's go. The first concept here is supervision, short for supervised learning. The picture is a stack of flashcards. On the front of each card is a question. On the back is the correct answer, written by a human. You show the model the front, it guesses. You flip to the back, and it adjusts itself to match. Do that across millions of cards, and the model learns to map questions to answers. That's supervised learning, training on examples that humans have labeled, input paired with the right output. The catch, and Chip names it directly, is that the labeling is expensive and slow. Every flashcard needs a human to write the back. If it costs a few cents and a few seconds per card and you need millions of cards, the bill and the calendar both explode. Hold on to that pain because the next concept exists entirely to escape it. For you, this shows up the moment you fine-tune a model or build a test set to measure quality. Both of those are supervised learning, and the cost and quality of your labels, your flashcard backs, quietly become your real bottleneck, exactly as Chip warns. The second concept is self-supervision, and this is the magic trick that made the whole field possible. So let me slow down. Supervised learning needed a human to write the answer on the back of every card. Self-supervision asks, what if the data could grade itself with no human at all? And for text, there's a beautiful trick that does exactly that. Take any sentence from the internet, hide the last word, ask the model to guess it, then unhide it to check. The answer was sitting right there in the original text the whole time. You didn't need a human to write it, you just covered it up. The text is its own answer key. That's self-supervision. The model generates its own labels from the raw data. And because every sentence ever written is now free training material, you can train on a staggering amount of text, effectively the readable internet. This is the engine behind what's called pre-training, the first and biggest phase of building a foundation model. Chip puts it simply, self-supervision lets the model learn from a huge pile of unlabeled data. Here's why this is the concept that unlocks everything else for you. Self-supervision is the reason general-purpose foundation models exist at all, the reason there's a powerful model sitting behind an API, an application programming interface, just waiting for you to build on top of it. You didn't have to label anything. The internet was the flashcard deck, and it wrote its own answers. Supervision needs human answer keys. Self-supervision invents its own. The third concept is log likelihood. And here's my first honesty flag. Chip assumes you already know this one. The book won't stop to explain it, which is exactly why I will, because it underpins how models are trained and scored. Start with the plain word, likelihood. The likelihood is just how probable the real answer was, according to the model. Go back to the bag of tiles. The true next word was blue. How big was the blue tile when the model reached in? If blue filled half the bag, the model assigned it high likelihood. It was confident and correct. If blue was a tiny tile, the model assigned it low likelihood. It was caught off guard. Training a model means nudging it over and over to make the true answers bigger tiles. So why log likelihood? Why that extra word log? Practical reason. A real sentence is many words, and you multiply all those tiny probabilities together, and you very quickly get a number so small the computer rounds it to zero and chokes. Taking the logarithm, log for short, is a mathematician's move that turns that runaway multiplication into a gentle addition that computers handle cleanly. That's the only reason it's there. Log likelihood is just likelihood made safe to compute. And one connection that'll pay off later. When you flip log likelihood negative, you get something the book does teach, called cross entropy, which we'll meet at the very end of this episode. They're the same idea wearing two outfits. For you, the practical handle is a thing called log probs, log probabilities, which many model APIs can hand back to you. They're your window into the model's confidence on each word, and you can use them to catch shaky, low-confidence outputs before they reach a user. The fourth concept is gradient descent, the actual procedure that trains a neural network. The book mentions it in passing and assumes the rest, so let me give you the real picture. Imagine a hiker standing somewhere on a mountain in thick fog trying to reach the lowest point in the valley. She can't see the valley floor. All she can do is feel the ground right under her feet and notice which direction slopes downhill most steeply. So she takes one small step that way, then she stops, feels the slope again, takes another small step downhill. Step after step after step, she descends to the bottom. That's gradient descent. The mountain's altitude is the model's error, how wrong it currently is. The lowest point in the valley is the model being as accurate as it can get. The downhill direction is the gradient. The the direction that reduces the error fastest. And training is just taking millions of tiny downhill steps, each one making the model slightly less wrong than the step before. Chip's one-line framing is that gradient descent is really a search through an unimaginably huge space of possible settings for the one that works best. You won't run this by hand, but it's the why underneath the dials you will touch when you fine-tune. Things like how big each step should be. Picture the hiker in the fog feeling for downhill. That's how every model on Earth got smart. The fifth concept is backpropagation, and it's the partner of gradient descent. So it follows naturally. Gradient descent says, step downhill. But a model has billions of internal knobs. To step downhill, you need to know for every single knob which way to turn it to reduce the error. Backpropagation is how you figure that out. The picture is blame assignment. The model makes a guess. The guess is wrong by some amount, and backpropagation walks backward through the layers of the network, from the final answer back toward the input, figuring out how much each knob contributed to the mistake. Knobs that pushed hard toward the wrong answer get a lot of blame. Knobs that barely mattered get a little. Now you know exactly which way to turn each one. Then gradient descent takes the step. Backprop is the blame, gradient descent is the step, and training is those two dancing together a few million times. Here's the part that matters for you, and it's a concrete one. To assign blame backward, the model has to remember everything it computed on the way forward, every intermediate scribble. That memory adds up fast. It's the direct reason training a model needs far more memory than simply running it. This is the exact cause of a wall you'll hit. I can run this model on my machine just fine, but the moment I try to fine-tune it, I run out of memory. Now you'll know why. Backprop's bookkeeping is the culprit. The sixth concept is the loss function, and the book mentions it only in passing. So here's what you need. The loss function is the model's scorecard. It's a single number that answers one question. Right now, how wrong is the model? Big number, very wrong. Small number, nearly right. And the entire point of training, the whole hiker in the fog descent, is to drive that one number down as low as it'll go. The loss is the altitude the hiker is trying to minimize. For language models, that scorecard is almost always the cross entropy we keep circling. The surprise meter we'll define properly in a few minutes. The point for now is just the roll. The loss is the thing training optimizes. And here's the judgment call that makes this an AI engineering concept and not just trivia. The loss is a proxy. It measures something easy to count. Was the next word predicted well? But that's not the same as what you actually care about, which is whether the answer is useful, correct, and safe for your user. A model can get a beautiful loss score and still be unhelpful in your app. That gap between the number training chases and the outcome you truly want is a theme that runs through the whole book, especially the 2 chapters on evaluation. Whenever you optimize a proxy, keep one eye on whether the proxy still points at the real goal. The 7th concept is hyperparameter tuning, and it hinges on one clean distinction. There are 2 kinds of numbers in a model, and people mix them up constantly. The first kind, parameters, are the knobs the model learns by itself during training. The billions of values backprop and gradient descent are busy adjusting. You don't set those. The model discovers them. The second kind, hyperparameters, are the settings you choose before training even starts, and the model never touches them. Chip draws this exact line. Parameter versus hyperparameter. The picture is baking. The ingredients reacting in the batter. That's the model learning its parameters, happening on its own inside the oven. But the oven temperature, the baking time, how big you scoop each batch, those you dial in from outside, before and around the bake. Those are hyperparameters, and tuning is exactly what it sounds like, trying different oven settings to get the best cake. The big ones you'll actually meet when fine-tuning are the learning rate, how big each of the hiker's downhill steps is, the batch size, how many examples the model looks at before each step, and the number of epochs, how many times it reads through the whole training set. This is hands-on for you. When you fine-tune a model, these are the dials you turn, and the model can't turn them for you. Set the learning rate too high, and the hiker takes giant reckless leaps and overshoots the valley. Too low, and she takes forever, or gets stuck. Knowing what each dial does is the difference between a fine-tune that works and one that quietly fails. That closes the machine learning family. Supervision and self-supervision are how a model gets its training data. Gradient descent and backpropagation are how it learns. The loss function is its scorecard, and hyperparameters are the dials you control from the outside. The third family is architectures, 3 different ways of wiring up a neural network. Only one of them runs the modern world, but knowing all 3 tells you why. A quick word on what architecture even means here. A neural network is layers of simple math units passing signals to each other. The architecture is the wiring diagram, how those layers connect, and which units talk to which. Change the wiring, and you change what the network is good at. There are 3 wirings on Chip's list. The first is feed-forward, the simplest wiring there is. Picture a straight assembly line in a factory. A part comes in one end, moves through station 1, then station 2, then station 3, and out the far end as a finished product. It only ever moves forward. Nothing loops back, nothing waits. That's a feed-forward network. Information flows in one direction, input to output, no cycles. In modern AI, you rarely meet a feed-forward network standing on its own. Instead, you meet it as a component living inside the bigger architecture we're about to discuss, where it shows up as the layer that does the heavy thinking, crunching the patterns the network has noticed. The detail worth carrying. A huge share of a model's knobs, its parameters, live in these feed-forward layers. So when you reason about how big a model is, how much memory it eats, and how much it costs to run, a lot of that weight is sitting right here in the plain forward assembly line. The second wiring is recurrent, and it's best understood as the thing transformers replaced. Picture someone reading a long sentence out loud, but they can only hold one sticky note in their hand. They read a word, update the note with a summary of the story so far, read the next word, update the note again. One word at a time in strict order, carrying everything they remember on that single note. That's a recurrent neural network, often shortened to RNN. The recurrent part is that loop. Each step feeds back into the next. This was the dominant design for language before 2017, and it had 2 crippling problems. First, that single sticky note. By the time the reader reaches the end of a long paragraph, the early words have been overwritten and smudged. The model forgets context from far back. Second, because it must go strictly one word at a time, it can't take advantage of modern AI chips, which get their speed from doing thousands of calculations at once. A reader stuck reading one word at a time wastes all that parallel horsepower. Why bother learning the design that lost? Because understanding why RNNs failed is the cleanest way to understand why the winner won, and why it costs what it costs. The newer architecture was built specifically to fix these 2 problems, the single sticky note forgetting and the one word at a time slowness. Keep those 2 failures in mind for the next 60 seconds. The third wiring is the transformer. And this is the big one. It's the architecture behind essentially every model you've used or will build on. The GPT family, Claude, Llama, Gemini, all of them. So let me spend real time here. The transformer's breakthrough is a mechanism called attention. Here's the picture. Imagine a dinner party where everyone is mid-conversation and someone at the table says, "Yeah, I returned it because it was broken." Instantly, without effort, every guest's mind flicks back to the thing being discussed 5 minutes ago, the blender, to make sense of it. That reflexive glance back to the word that gives meaning to the current word, that's attention. Let me make it concrete with the sentence Chip uses. The cat sat on the mat because it was tired. When the model reaches the word it, what does it point to? The cat, obviously. Mats don't get tired. You know that instantly. But for the model to know it, while it's processing it has to look back at every earlier word and decide which one matters most for understanding it. Picture lines reaching from it back to each previous word, and the thickness of each line is how much attention it's paying. The line back to cat is thick and strong. The lines to mat and the are thin wisps. The model has worked out with math that cat is what it means. Now watch how that one mechanism solves both RNN problems at once. The forgetting problem, gone, because every word can reach directly back to every other word, no matter how far apart, with no single sticky note getting smudged in between. And the slowness problem, Gone, because all those attention glances for every word looking at every other word can be computed at the same time, in parallel, which is exactly what modern AI chips are built to do. Better memory across long distances, and a design that flies on the hardware. That combination is why, within a few years of its introduction, the Transformer took over everything. First language, then images, audio, and multimodal models that handle several at once. But that same all-words, look-at-all-words design has a price, and it's a price you'll pay in your applications. If every word attends to every other word, then doubling the length of the text roughly quadruples the amount of attention work. It grows with the square of the length. Picture the dinner party again. 10 guests is 45 handshakes, but 100 guests is nearly 5,000. That's why long prompts and long documents get expensive fast, why models have a maximum context length at all, and why an entire chapter of the book is devoted to making inference, running the model, cheaper and faster. Every one of those topics traces straight back to how attention works. So, of all 19 concepts, the Transformer and its attention mechanism give you the most leverage. Picture the dinner party glancing back at it. The fourth and final family is metrics. 6 ways of keeping score, of measuring whether your AI is actually any good. There's no single chapter that lists these together because the right ruler depends on the job. And picking the right ruler is itself a core AI engineering skill. Measure the wrong thing and you'll happily ship something broken. The first 4 metrics, accuracy, precision, recall, and the F1 score, go together as a set, so I'll teach them as a little group. Then we'll finish with 2 specialists, Cosine similarity and cross entropy. The first metric is accuracy, the most intuitive one and also the one that lies to you most often. Accuracy is simple. Out of all the predictions, what fraction did the model get right? 100 questions, 80 correct, 80% accuracy. Chip defines it plainly as how many the model gets right. Here's the trap, and it's a famous one. Imagine you build a model to detect a rare disease that shows up in 1 person out of 100. A lazy model that ignores every input and always says healthy will be right 99 times out of 100. 99% accuracy. Sounds spectacular. It's useless. It never once caught the sick person, the only thing you cared about. That's the lesson. Accuracy is honest only when the categories are roughly balanced, and every kind of mistake costs about the same. The moment one outcome is rare, or one mistake is far worse than another, accuracy becomes a comfortable lie. And that is precisely why the next 3 metrics exist. They were invented to catch what accuracy hides. The second metric is precision. And here comes a warning, because this word means 2 completely different things in this book, and confusing them will cost you. The metric precision asks, of all the times the model shouted yes, how often was it right? Picture a spam filter. It flags 100 emails as spam. You check, and 90 of them really were spam, but 10 were real messages it wrongly condemned. Its precision is 90%. Precision punishes false alarms, crying wolf. High precision means, when this thing says yes, you can trust it. Now, the warning. Elsewhere in the book, in the chapters on making models smaller and faster, you'll see the word precision constantly, in phrases like lower precision or precision bits. That is a totally different meaning. There, precision is about numerical precision, how many digits of detail you use to store each of the model's numbers, and it has nothing to do with measuring accuracy. Same word, 2 unrelated worlds. When you see precision, check which room you're in. Are we keeping score, or are we squeezing the model smaller? Don't let them blur. For your work, you reach for the precision metric when a wrong yes is expensive. A guardrail that blocks user content, for example, you do not want it falsely flagging innocent messages, so you tune it for high precision. When it says block, it had better be right. The third metric is recall, the natural partner to precision, and it has its own warning too. Recall flips the question. Instead of, when I said yes, was I right? Recall asks, of all the things I should have caught, how many did I actually catch? Back to the spam filter. Suppose 200 spam emails came in today. The filter caught 160 of them and let 40 slip into your inbox. Its recall is 80%. It caught 80% of the spam that existed. Recall punishes misses, the ones that got away. The book's own definition in the retrieval setting is the fraction of the right items that the system actually found. The warning here is smaller but sneaky. The everyday word recall, as in recall that we discussed this earlier, shows up all over the book as plain English. Don't mistake those friendly reminders for the metric. The metric is specifically about the fraction you caught. You optimize for recall when a miss is the costly mistake, a safety filter screening for genuinely harmful content. You would rather it overflag and catch everything dangerous than let one harmful item through. That's high recall. And now you can feel the tension. Precision and recall pull against each other like two ends of a seesaw. Make the spam filter trigger happy to catch every last spam. Recall goes up, but it starts flagging innocent mail, so precision drops. Make it cautious to avoid false alarms. Precision goes up, but more spam sneaks through, so recall drops. Almost every classifier you build lives somewhere on that seesaw, which brings us to the metric that balances it. The fourth metric is the F1 score, and the book assumes you know it, so here's the plain version. The F1 score is a single number that balances precision and recall, so you don't have to stare at the seesaw and juggle two numbers at once. It combines them in a way that rewards having both reasonably high and punishes you for letting either one collapse. You can't game it by acing precision while recall falls apart, or the reverse. So the F1 score is usually the honest single headline number for a classifier, a spam detector, a content tagger, an information extractor. When you need one number to say, is this thing good? And accuracy would mislead you because your data is lopsided. The F1 score is the one to report. And because it's built from precision and recall, a low F1 immediately tells you where to look, which side of the seesaw is dragging. The fifth metric is Cosine similarity. And it's the quiet engine behind a feature you're almost certainly going to build. To get there, one quick idea: an embedding. A model can turn a piece of text, a word, a sentence, a whole document, into a long list of numbers that captures its meaning. Think of that list as an arrow pointing in some direction in space. Texts that mean similar things get arrows pointing in similar directions. I love this movie. And this film is wonderful point nearly the same way, even though they share almost no words. Cosine similarity is how you measure whether two arrows point the same way. Picture two compass needles. If they point in exactly the same direction, they're perfectly aligned, and the score is 1, identical meaning. If they sit at right angles, pointing in unrelated directions, the score is 0, unrelated. The further apart the needles, the lower the score. Chip's own example, two embeddings that are exactly the same score, a 1. Notice it's about the angle, the direction the arrows point, not how long they are. Here's why this is not abstract for you. Cosine similarity is the core operation inside semantic search and inside RAG, retrieval augmented generation, the technique where your app looks up relevant documents and feeds them to the model. The recipe is: turn the user's question into an arrow, then compare it by cosine similarity against the arrows for every document you've stored, and return the ones whose arrows point most nearly the same way. That's how Find Me the relevant passages actually works under the hood. So when your search feature returns junk, or your RAG app pulls up irrelevant context, you are, whether you realize it or not, debugging embeddings and cosine similarity. Picture the two compass needles. The sixth and final metric is cross entropy. And it ties this whole episode together because it's the same idea as the log likelihood we met earlier, now wearing its everyday clothes. Picture cross entropy as a surprise meter. As the model reads real text, the meter measures how surprised it is by each actual next word. If the true next word was a fat tile, the model expected low surprise. The meter barely moves. If the true word was a tiny tile it never saw coming, high surprise, the meter spikes. Cross entropy is the model's average surprise across a lot of text, and lower is better. A model with low cross entropy is rarely surprised, which means it predicts language well. Two connections close the loop. First, this is exactly the negative log likelihood from earlier. The surprise meter and the confidence meter are the same instrument read from opposite ends. High confidence in the right answer is the same as low surprise. Second, cross-entropy is the standard scorecard, the loss function, used to train language models in the first place, and it has a close cousin you'll hear named perplexity, which is just cross-entropy rephrased. The reason this earns a spot on your list, cross-entropy, and its cousin perplexity, let you compare base models and sense when a model is a poor fit for your particular domain. If it's constantly surprised by your kind of text, it doesn't know your world well, and there's a practical gift here. Cross-entropy needs no human-labeled answer key. It just needs text and the model's own predictions. That makes it a cheap signal you can compute without paying for labels. Useful both when choosing a model and when monitoring one running in production. That completes the metrics family. Accuracy is the blunt fraction right. Precision and recall are the two ends of the seesaw. The F1 score balances them. Cosine similarity measures meaning by the angle between arrows. And cross-entropy is the surprise meter that doubles as a training scorecard. Let me recap all 19 fast as a string of pictures so they stick for the walk home. The probability family. The model rolls weighted dice. Sampling, reaching into a bag of word tiles, bigger tiles more likely. Temperature is how hard you shake it. Determinism, the calculator your code is, versus the slot machine a model is. Distribution, the whole skyline of word likelihoods, which temperature flattens or sharpens. The machine learning family, how a model learns. Supervision, flashcards with human written answers on the back, expensive to make. Self-supervision, the text grades itself by hiding its own next word, which is how models read the whole internet. Log likelihood, a confidence meter for how big the right tile was, logged so computers don't choke. Gradient descent, the hiker in fog stepping downhill toward lower error. Backpropagation, assigning blame backward through the layers, and the reason fine-tuning eats so much memory. Loss function, the single how wrong am I scorecard the training drives down, and a proxy you must keep honest. Hyperparameter tuning, the oven settings you choose from outside. Learning rate, batch size, epochs. The architecture family, 3 wirings. Feedforward, the straight assembly line where much of the model's weight lives. Recurrent, the reader with one smudged sticky note who forgets and can't go fast. The design transformers replaced. Transformer, the dinner party where every word glances back at every other word through attention, which fixed both problems and now runs everything at a cost that grows with the square of the length. The metrics family, keeping score. Accuracy, fraction right, but a liar when data is lopsided. Precision, when it says yes, is it right? And watch out, the same word also means numerical detail elsewhere in the book. Recall, did it catch them all? The F1 score, one number balancing the precision recall seesaw. Cosine similarity, the angle between two meaning arrows, the engine of search, and RAG. Cross entropy, the surprise meter, the same thing as negative log likelihood, and the scorecard models train on. That's the list. 19 concepts, 4 families. Everyone now a picture you own, rather than a word that stalls you. When you open the book, you'll feel the difference fast. The early chapters lean hard on the probability family and the transformer. That's where sampling, distribution, and attention do their heavy lifting. The evaluation chapters run on the metrics family. Accuracy, precision, recall, the F1 score, and cross-entropy. And the chapter on fine-tuning is where backpropagation, the loss function, and hyperparameters come back to do real work. You'll meet each of these again in context, but now you'll meet them as old acquaintances, not strangers. That's the head start. Go read.